I'm Gary Edwards. I'm president of Peachtree Section, Mercedes-Benz Club of America, and I welcome you to our tech session tonight. I also have with me Ruben Howard, our vice president and also associate editor of Star Magazine, who's helping run the session. There's Ruben. And we also have one of our board of directors members who's I'm sure is going to come in a few minutes, Dean Prince. I don't see him up right now. All right, well, let me transition to introducing our guest speaker. If you remember last time I did this, this is about where my computer died, so hopefully it won't die today. But Lake Speed Jr., you might recognize that name because his father was a famous NASCAR racer, and Lake was following the footsteps of being in motorsports. He's very experienced in that area. He ended up working for Joe Gibbs Racing at a time when they were having issues with oil. And as a tribologist, Lake was the one that kind of saw their oil problems by coming up with the appropriate formulation. For those of you that joined us at our last tech session, we talked a lot about the appropriate oils and the differences between oils and why oils aren't necessarily backwards compatible. And you can go and see that on our YouTube channel. We did record that. Subsequent to that, Lake is now the vice president at Total Seal Piston Rings, and I believe his daughter also has a company that does oil analysis now. I first met Lake about 2014 when he was talking about oils and oil analysis, and I've been doing oil analysis on all my cars since then because I very quickly learned how important it was to gauge how your engine's doing and how well your oil is doing. And I actually took a course from Lake about oil analysis as well. And this is a topic that I've been wanting to bring to MBCA members for a long time. So I really appreciate Lake being willing to spend the time to do this. Lake is not only exceedingly knowledgeable in this area, he's also a wonderful presenter. He can present complex concepts in a way that makes it really easy to understand, and he's just fun to listen to. So Lake, thank you for being with us tonight. I know you're on travel, so thank you for taking time out of your busy schedule to talk with us. Over to you.
No pressure there, right? I have some big shoes to fill now, and unfortunately, hope everybody can hear me pretty good. I've been struggling with laryngitis for a couple of days, and out here in Arizona, it's really dry. So I'm trying to drink as much water as I can and keep things going. So we'll cross our fingers that the voice can make it for 60 more minutes. So we can get through all this and hopefully leave everybody in better shape and understanding how to utilize this incredibly powerful tool. So I'm going to see if I can share my screen here. And I want to go and show desktop 2. I hit share. And you're going to see what looks like SAP over there, because that is SAP. But then I'm going to click this button.
I see oil. Yep.
All right. Success. Isn't it nice when technology works the way you expect it to? All right. So what we're going to talk about tonight is kind of the do's and don'ts of used oil analysis. So as Gary mentioned, my daughter does have a used oil analysis company that she helps me with, and actually my son's involved now too, which is great. And we started that several years ago just because me personally, I got frustrated with some of the quirks that are amongst the different labs. I don't have anything bad to say about other labs at all. In fact, one of the things we'll tell you later on is pick a lab, stay with it. Don't jump all around, looking for the better deal or the trick of the week type thing. Just pick one, stick with it. Whichever one you want to do is fine. I'm just the super uber nerd when it comes to this stuff, and I want what I want. So I did my own so I could get it the way I wanted it. But that's enough about that. We won't talk anymore about that. All right. So as he mentioned, my dad is Lake Speed, the NASCAR or former NASCAR driver, and I worked at Joe Gibbs Racing, and I'm a member of a group called the Society of Tribologist and Lubrication Engineers. Within that group, I'm a certified lubrication specialist and a certified oil monitoring analyst. So analyzing oil is what I've been trained to do and been doing it for well over 15 years at this point. And it's been a lot of fun, and even it's a very useful tool here at Total Seal. Essentially, The piston ring is your oil's best friend. What kills engine oil is fuel dilution, blow-by, heat, and the piston ring is the physical barrier between the combustion and the intake stroke, where you get all the fuel and everything coming in, and your oil. So as a tribologist, piston rings and motor oil go hand in hand. And it's one of the key things to keep in mind that not to give away the whole show here at the very beginning, but in my years of doing oil analysis, the number one reason for we'll call it a poor result, what happens more times than not, isn't choice of oil. Now that does happen, and we've seen it. In fact, we can maybe tell that story later about that customer from last year, right? And what he changed, on his Mercedes and what came about. But more times than not, fuel dilution is the key problem. And so being on the lookout for fuel dilution, managing that is going to be the first tool you want to use in order to extend the life of your engine and get the least amount of wear, best oil life as well. So all that can save you money in the long run. So that being said, we'll go ahead and kind of get going. But before we get too deep into it, I am a Mercedes-Benz owner myself. That is my great-grandfather's 240D 1983 edition that my grandfather had for a short period of time. Then my mom had it for a long time, and I've had it for the last 7 years, and it's my airport car. That's the car I drive to the airport, and I've tried to get my other kids who want to drive it and do all that, but they don't like the fact that it's a stick shift. It's a diesel, and of course, I love it for both of those reasons. So it's actually one of my favorite cars, and my kids hate it. They hate it to death, but I still love it. And in case anybody's wondering, if you happen to be a NASCAR fan and all that, Dad's still doing great. You guys are the Peachtree section, so you're in Georgia, and that's me and Dad. We were actually down in Barnesville, Georgia, earlier this spring. Now these results are from a couple of years ago up in Ohio, and yep, that's Dad. He's still faster than me, and guess what? That was still the case, even last month. Even though I won the race, that's only because he got crashed out. Now, I didn't crash him. Well, I didn't crash him the first time. No, actually, I did crash him the first time. I didn't crash him the second time, and it was a mistake on the first prime. I would never try to wreck him, but he's still faster than me. His time sheets were still about 2/10 faster than me. So at 74 years old, the guy can still wheel it and still have the passion to go out there and do it. So if there's any Lake Speed fans out there, just know Dad's doing great, still having fun, and maybe one day I might be able to outrun him. We'll see. So the little background story, which we mentioned at the very beginning, the real history from my experience in usual analysis goes back to Joe Gibbs Racing. As we mentioned earlier, we had camshaft problems, and this is in 1999. Ended up costing us the championship that year, and we found out it was the engine oil that was the problem. Specifically the levels of ZDP, the zinc dialkyl thiophosphate, in the oil, and that there was a company called Lubrizol that actually made that product. And we began working with them, and we developed a break-in oil, developed assembly lubes, developed a race oil, and in 2000 we won our first NASCAR championship. The significance of embracing tribology, which tribology is just a fancy word for the study of friction, wear, and lubrication. So we employed all of that. We didn't just change the oil. We looked at coatings, surface finish, and we measured that using tools like used oil analysis and using profilometers to measure parts. And so we did all this. And the 8 years prior to Joe Gibbs Racing embracing tribology, the team won 0 championships and 17 races. In the 8 years following that, we won 3 championships, and we won over 40 races. So it was a significant change in the performance of the team just based on embracing that science. And why I go through all this is to say that throughout that process, and even to today, 22 years later, they're still taking oil samples every single race, and we're analyzing and we're looking at it and we're making decisions. And even this last week, we found, hey, there's one engine that the wear metals were significantly higher than all the others. So that's an engine that needs to be inspected further and before it ever goes back to the racetrack again, because we're in the world now in NASCAR where all the engines have to run more than one race. It's not like it was 22 years ago where you could run one engine, one race, and completely rebuild it. Today, the engines have to be presented, they're sealed, and they run multiple races. Sometimes could be, it's at least 2. Sometimes it could be 3 or even more, depending upon what series you're in order to make that happen. So the key tool we're using between multiple races is used oil analysis. So that's kind of being the kind of the linchpin of this whole thing. Is it's a tool for letting you know how your engine is doing. And let's also not just stop on the fact that it's just engine oil. You can apply this to engines, transmissions, gears, all of it. And they all have their own unique characteristics. And just as a tribologist, this is my public service announcement. Don't ever put anything in your oil. If you think your oil is deficient in some way or another, you should use a different oil. And you should probably never use an engine oil in a transmission or a gear oil in a transmission or vice versa. They all lubricate, but they're each chemically designed for the needs of that application. And understanding that application is the real key to building the correct chemistry for it. And it's also a key in looking at the used oil, of understanding, well, what's normal for this environment? Because a racing environment is going to give you a different set of normal than a passenger car environment is going to be, than a diesel engine oil, for over-the-road truck type diesel. They're all going to be different based on that environment. So you got to begin with that understanding of what this looks like. So the concept of used oil analysis is pretty basic. Just like when you go to the doctor and you have a checkup, what do they normally do? They take some blood and then they take it back to the lab and they analyze it. And then they kind of see, okay, where do your different levels? I got a thyroid condition, so I have to go every year and they take the blood and they check my thyroid levels, and then we trend it over time too. All right, so that's really what we're going to be doing, the exact same thing, as opposed to taking blood out of your body. We're taking the lifeblood, you will, out of your engine, which is the engine oil. And then we're going to be able to tell from that if there's any contaminants in there and things like that. And the reason for doing it isn't just to know, hey, is my engine okay? Because the engine could be running fine. You think, okay, my engine's fine. It's running fine. Not hearing any knocks or anything. Or my engine blew up. What happened? Well, those are two extremes. What I really want you to think about is understand that most things in life aren't black and white. There's not this end of the continuum or that end of the continuum, and there's nothing in between. Just kind of like in school, you could pass the test. Just because you pass the test mean you got an A. Could be a B student, could be a C student, could be a D student. You don't know. You just know you passed. And what I mean by that is, if your engine is running and it's not making any noise or anything weird, it's like you passed the test, but you don't know if you're a D student, a C student, a B student, or an A student. How are you doing in terms of the health of that engine? How's that oil performing? Is it really giving you what you believe it's doing? And, as someone that was in the oil industry for so long, selling other oils and brands and stuff, that was the most frequent thing. Well, I've always used X and I've never had a problem. You could be a D student the whole time and just not know it. Not to be offensive to anybody, but that's what you come across a lot of times. And then all of a sudden you start doing oil analysis and you're like, whoa, it's really different. And you can start comparing then you can really get it. So the idea is it's a tool that you want to be able to use as a yardstick, ultimately to be able to improve it, especially if you have a classic car and you're trying to extend the life of that car. You want to make sure you're doing all the right things. And this is a tool you can use to do it. And just to kind of back that up, all right, so let's look at, does it really correlate to wear? Like if I see something on that report, how much confidence can I have that it's really there? Well, you can look right here, a couple of bearings. So this is from a bearing test we ran years ago when we were at Gibbs. And you can see that the bearing on top obviously is worn more than the bearing on the bottom, right? You don't need any inspection equipment to see that difference. But you take the oil analysis, and a typical bearing, a tri-metal bearing, is made of copper, tin, and lead. So you can look at that oil analysis report and say, all right, let's look at those wear metals. Look at those levels. So I have 27 total wear metals between the copper, tin, and lead on the upper bearing, where you're at 16 on the one below. So you can see the difference right there. Next one, camshaft. So when I was at Gibbs, we were developing oils, one of the things we would do is we would do wear tests. And we talk about ZDP, as a anti-wear additive. Well, there's more than one. There's more than one manufacturer, and there's more than one type. So when you're evaluating the performance of these, we had to find a way to do that. And we did it via camshaft testing. We would run these flat tappet camshafts, and we would use a profilometer. And that's what you're looking at. You're looking at a profilometer trace. You can measure in millionths of an inch the wear scar, if you will, over the nose of the camshaft. And you can see that area of wear on both camshafts. And those are two different ZDPs, same amount. And we can physically measure that wear. Well, then you go to the lab report from those same samples, and you can see that the ZDP-A that had the smaller wear scar had only 5 parts per million of iron in it, whereas the one with the larger wear scar had 10 parts per million of iron. Well, iron is what's in those camshafts. Those are cast iron cams. What's also interesting, if you look down at the lead, there's no lead in the camshaft, but 2 parts per million lead with sample A, and there's 6 with sample B. That's because lead is soft, and it's in the cam bearings, and it's in the main and rod bearings. As you put more wear metal into the oil filter does not catch everything. Let that sink in for a second. There's a filter, and it does catch stuff, and filters are good. But filters are not 100% effective, typically on very small particles. And these particles right here, because oil analysis can only see particles about less than 10 microns. Well, most oil filters don't really capture much of anything under 20 microns. So that wear metal that's getting through that filter is causing abrasive wear throughout the engine. And you can see that the aluminum is higher with ZDP-B than ZDP-A, because the more cam wear that occurs, those hard iron particles propagate through the engine and cause more wear. So that's why it's so important, is you don't want that knock-on effect of increased abrasive wear, because your oil may not be doing the best job it could at protecting the harder components, say like the camshaft. The valve train is typically going to be what wears first, and that's because the valve train moves at half the crankshaft speed. So it's moving slower. So in lubrication, we use a thing called the Strybeck curve, which I didn't put a slide for, but maybe I should have. But you can bear with me. The idea in lubrication is we have 3 stages of lubrication. We have boundary, mixed, and full film. And if you've ever been water skiing or seen someone water ski or understand the concept of water skiing, you'll know that when the boat is stationary, it's not moving, the skier is in the water. Then as the driver of the boat accelerates and it begins to drive away and the boat gains speed, it begins to pull the skier out of the water. the skier doesn't go from just being in the water to on top of the water. There's a transition point where the skier's somewhat in the water, somewhat out of the water, they're coming up. We call that mixed film. And then you've got the skier riding on top. That's full film lubrication. So the engine valve train operates in that boundary condition, which is the skier in the water. Because the Stribeck curve uses a calculation, which is the viscosity of the oil times the speed of the components divided by load. And in the valve train, you have static pressure from the valve springs, and you're running at half the crankshaft speed. So it's slower with more load. So that's where the valve train wear tends to be the thing we focus on the most, because that's where most of the wear is going to occur in the valve train first. It's going to propagate out. Your piston rings also operate in all three stages of lubrication every single cycle, because the piston has to stop at the top and at the bottom, which is why there's more cylinder bore wear at the top, because that's the highest load pressure, lowest speed, slowing down, and then full stop at the top. So the idea you want to look at is that iron's really important, because it's going to come from the cylinder bore, come the valve train, because it's that boundary condition. So that's really the tail of the tape, for the most part, of the engine oil's performance. If you're throwing a high iron level, then you know that you're getting cylinder bore wear, you're getting valve train wear, and ultimately that's the life of your engine. So the idea is you want to get a hold of that and make sure we're measuring that and get the lowest amount of iron that you can. And so oil analysis kits. Now, again, I don't care who you buy them from, doesn't matter, but they should all come pretty much with the same thing. You're gonna have a sample bottle, and you're gonna have a registration form, some way of getting the lab the information to know what to do with your sample. And then you're gonna have a postage page mailer to send it back to the lab, right? So those are the kind of the basic things that should show up in every oil analysis kits. All right, so once you have your kit, here's the things that you wanna do and the things you don't wanna do. And we'll go through this real quick, and then we'll cover each of them in detail as we move forward. You do want to take samples on a regular basis. You also want to take a fresh sample of the oil you're using. That's really important to have that baseline. You want to use the sample bottle that's being provided, not use your own. And gentlemen, I know this can be tough sometimes. We need to follow the instructions provided in the kit. You would be amazed, well, you may not be amazed at how often my daughter is incredibly frustrated that people send in samples and we have no idea who sent it in. The instructions are clear in the book of what to do, but they didn't read that. They just took the sample bottle, put it in the thing, and sent it in. We have no idea who you are. And we wait. Then someone calls up eventually, I sent that sample and I never got my report. Well, did it? What number was it? Oh, I can't remember. But you find it out and you eventually take care of them and get it sorted out. But it's the bane of her existence. She complains all the time because people, they don't read the results or read the instructions, I should say. And you also want to make sure that you take samples from the other things besides your engine, right? So with transmissions now being filled for life and things like that, you might want to be able to take some samples. You can do that during a vacuum pump. There's not just, you don't have to drain the oil always to do that, and just to kind of check on, see what's happening with the other units, especially if you're purchasing a new vehicle or a used vehicle. It's a great way to check out the health of all that and see what's going on. Is check transmission, check the rear end, and make sure everything's in good shape. Now, with those things being said, the things you don't want to do is you don't want to, one time, taking a drain sample, but now I'm going to change my mind and I'm going to start doing a vacuum pump. And then I'm going to go back to the drain sample because I couldn't find the pump today and do that. You want to take the sample the same way. You want to get in the same procedure, right? So If you change oil yourself at your house, you may want to find a loop in the neighborhood. Say, yeah, I'm going to drive the car, this many times across the loop. Then I'm going to come back and I'm going to have all my stuff set up beforehand before I take the car out for my drive and come back. Because you want to make sure you're doing the same procedure so that the amount of time that the engine sits before the oil is trained is the same. Because if you take a sample 5 minutes after the engine shut off, you'll get a different result than if you wait 5 days to take the sample. So it's important to know these little different details. And the other thing too, don't jump from lab to lab. Pick a lab, stick with them. Because we're going to talk about that in a little bit. It's important not to just jump around, and we'll explain why in a little while. Also too, don't read too much into a single number. Like, don't panic if there's one number that seems a little bit out of line. So people tend to fixate too much on a single number, whether to the good side or the bad side. It's a report. It's a full sample of a lot of different things. You want to look at everything as a whole and use that to determine how you feel and how to move forward. The last thing is, don't expect, Perry Mason, or for the younger folks, CSI. If your engine blew up, take a sample. It's probably going to tell you what you already know. It blew up. Now, that being said, there are some cases where you say, oh, look, there's a ton of water and glycol in there. Obviously, you overheated the engine before it blew up. That's what caused it to throw the rod out the side, is you actually lifted the head gasket slightly first, and that put a bunch of water into the cylinder. That caused it to hydro lock, which knocked the bearing out, which went to the side of the oil pan. Okay, so it does happen. You can back it up. I had a guy today, I sent a report to this morning, that had a high level of fuel dilution. And this is a car he was, had done a pre-purchase inspection on. Well, sure enough, he had this commentary from the previous owner that he had taken the car to last time the car had been out, he'd gone to Watkins Glen, tracked the car. It was running a little bit rich, so he changed the tune in it and all that. Well, guess what? The narrative that the guy who was selling the car told the purchaser completely matched what we saw in the oil analysis results. So there are some times that you can get that feel-good moment, but know that most of the time this is data mining. It's about trend analysis and building the picture over time, not just the aha, I got you moment. We love those. Those are really fun, but don't go into expecting that. Okay, so let's keep moving forward here. Okay, as we mentioned, taking the samples on a regular basis, that trend analysis we were just talking about, that's the key thing. And with your lab, you should be able to tell them the sample unit number, and they should be able to send you a report with that sample history. So you don't have to go back and make your own Excel spreadsheet if you want to, but the report itself should have that history on there, and you should be able to see it. Like in this case, these numbers are dropping. This is the older ones on the bottom, newer ones on the top. And this is a brand new unit from break-in. So there's always more wear at break-in. Know that. That's the highest normal you should ever see, which is why taking a break-in sample of the new engine is so important, because that sets the high watermark, if you will, of what that engine should see as normal. That way you're not worrying about other standards and references that are based on a whole bunch of different engines. This is your engine, the way you drive, and in your environment. What's normal for your engine? So that's why it's really great. Some people say, well, I don't want to take a sample at break-in. It's just going to be high. Well, yeah, that's the reason why you want it, because it's the normal level of high for your engine. It should go down over time, which is what you see here. Everything here is totally good, green, things are great. That trend analysis can also tell you in terms of how far can I go on my oil drain. Now, this is a racing engine application, but the logic still holds true that if you're trying to extend the oil drain, you don't want to increase wear metals of your engine at the expense of the oil change. And in this case, you can see 135 laps versus 251 laps. But we're seeing here is the wear metals, iron's at 10, aluminum's at 10, but they jumped to 21 and 22. But if you do the math, if we doubled the wear metals, didn't double the mileage. Okay. Well, it's 270 then double the mileage, but those numbers would have been more than double. They already are. They'd be even more than double. So maybe 135 is too short. 250 is too long. Maybe 200 is the right. So this is the way you can use that tool to dial in the correct drain interval in order to get the most bang for your buck out of your oil change without costing the engine. Now, this is from my Porsche that I have from brand new. It's one of Jake Raby's engines. And you can see where the total wear metals were, but I always do, I take that total wear metal and I divide it by the number of miles. That way I can normalize things. Now, the trick is, if you're dividing by 1,000 miles, you got to make sure that you have at least 1,000 miles sample. If you're taking the sample for less than 1,000 miles, that same math artificially inflates the wear rate. So you got to be careful for that. So we normalize it this way, and you see at break-in, it was the highest at basically 18.6 parts per million of wear metals per 1,000 miles. And then it dropped and it dropped. And then we changed the oil. We tried something completely different, and it didn't like it very much. And then we changed to a different oil, and it got better, and went to that same one again, and it continued to get even better. And that's one thing to kind of point out, that when you change brands of oil, it is normal for the wear to be, I'll call it, elevated during that transition. Because what you're doing is you're changing the chemistry. And think about the engine oil, the additives in your oil. And the oil is a delivery device for those additives. Those additives just in the bulk of the oil don't do your piston rings or your camshaft any good. They have to leave the oil and get onto the surface and create the sacrificial coating that protects those surfaces. So when you're changing chemistry, you're removing that previous coating and you're replacing it with a new one. And so it's normal for there to be an uptick initially and then a drop when you make a change. Now, some chemistries they get along super great, and it's just kind of like, oh, we're good. Blend right on, we're fine. Other ones, they're more aggressive to each other. They don't like it. So just know that sometimes it takes 2 samples, even 3 samples on a new oil to really figure it out. And you can see that right here, right? That things were going pretty good. We made a change. Actually, I did a flush right there. But then that second sample was better than this sample. Same oil. Why? It's settling in. You're not changing it, creating any kind of additive clash or carryover effect has been reduced that way. So keep that in mind. Next thing is take that sample of the fresh oil. That way you know what the additive package looks like in your new oil, which also can be helpful for detecting cross-contamination. So if the previous oil, like this is something we see all the time, there are several Castrol products that contain titanium as an additive, very small levels of titanium. Titanium can also be a wear metal. Now, most engines don't have a lot of titanium parts, but they're there. Well, if someone, say they send in a sample of what's called this brand X oil, and I see that, their engine doesn't really contain titanium parts, but there's 20 parts per million of titanium in the oil. Am I going to flag it for wear? No. What I'm going to do is I'll still let it be highlighted that it's, abnormally high for wear. But in the comments, we'll say, hey, listen, any chance the previous oil was Castrol? Or I think there's another one, Kendall uses that. I'll ask them the question, because I really think that's the key thing, is when we find something that's out of line, it shouldn't be the analyst trying to read tea leaves and tell you what he thinks happening. It should lead to questions. hey, maybe this did happen. Is there any validity to this theory or ability? And let's create a conversation around that component or issue, and let's figure out what's going on. In that previous case with the titanium deal, had it happened several times. Like, oh yeah, the dealership was changing it before when I think they used Castrol. Yep, that's what it was. It was the residual Castrol still in the engine that was causing high titanium. 2 samples later, it's all gone. So there wasn't a valve retainer problem or something else like that going on. It was just the carryover effect that when you change that oil, you're not getting it all out. It's still on the surfaces. So just know that going into that, which is why it's helpful to have a sample of the new oil you're going to, so you can compare the two. You can see the viscosity change. You can see that maybe additive carryover effects. It's really helpful to know that. As we mentioned, you definitely want to use the sample bottle provided in the kit and not your own. This is real world, not making this stuff up. It's been sent to us, right? And you're like, they sent us a sample in a Gatorade bottle, and it's like, man, it's positive for potassium and sodium. Well, do you have a coolant leak, or did you use a Gatorade bottle that wasn't cleaned out very well? I think we know the answer. We're not going to sit there and say you have a coolant leak and you got a problem. No, you contaminated your sample and how you handled it. And we've seen that before, taking a sample from the drain pan and pouring that into the jug. Nope, don't do that. That's going to cause contamination. So that's why it's really important, to follow the instructions. The instructions in the kit are going to tell you exactly what to do. And if you follow those, you're going to more likely get reliable results, consistent results, so that your trend analysis is telling you the picture that you hopefully want to be seeing. So just going to keep that in mind. And then, as we mentioned before, it's not just engine oil you can do this with. You can do it for engine transmissions, rear gears, especially dual clutch transmissions. If you got modern cars with DCTs, it's a really good idea to check these, because the life of that transmission will be based on the wear metals in that transmission. It will affect the clutches. It will affect the gear teeth wear. So it's a good thing to use this tool, not just for engines. Now, we talked about the sampling procedure. So at Joe Gibbs Racing, there's a race after the race, that once the race is over and the drivers are done their job, that's when the mechanics are all racing to get home. They've been gone for several days. They get one day off. They want to get back home and take as much of that day off as they can. So they're in an absolute thrash. So guess what? No one's doing at the racetrack after the race. No one's taking oil samples. Cars are going in the trailer and they're going home. So what we're doing is we're taking the samples from the cars back at the shop. And what the difference here is, if that engineer, when he drains the sample of gear oil, this was a gear oil sample, by the way, into the container, if he just takes that container and pours it straight in to the sample jar and sends it to things up to the lab, you're going to get 24 parts per billion iron. Take that exact same sample, shake it up, pour it in a sample jar, I get 75. Well, 24 is not a problem. 75 is. So it's really important to make sure that you take the correct sample procedure that is going to give you a representative sample of what's in your engine or transmission. And the best way to do that, as we kind of mentioned earlier, take a car out for a drive, get everything moving around, all mixed together, warmed up, have all your stuff ready before you leave. So when you get back, put it up on the ramps, wherever you're going to do, your tools are already there, clean around the drain plug, so we're not getting road grime and stuff into the sample. Clean around that, crack it, have your drain pan ready, have your sample bottle ready. Pull the drain sample plug out. To Mississippi, through Mississippi, put it in the stream, take the sample, till the bottle's about 3/4 way full, pull it out, off the stuff around the sides later. But that will give you a representative sample because the engine, transmission, or whatever has been warmed up, it's agitated, and you've taken the sample midstream. That's the best way to take a drain sample. If you do that every single time, your results will be consistent. You can have confidence that any variation based on something real that's inside the engine. And this is really important because this is why we say, don't jump from lab to lab to lab. You can take the same sample and send it to 3 labs, and you're going to get some variation from lab to lab to lab based on the equipment, because not everybody runs the exact same brand of equipment. They don't have all the same lab techs. They don't all calibrate the exact same day at the exact same time. So there can be some variation, and it could be important depending upon what it is. You look at the phosphorus levels from lab C versus lab B. If, let's say, the new levels are supposed to be up here, and I'm looking at this, I'm seeing, I could read in consumption. And usually when an engine is in the early stages of distress, you'll see phosphorus consumption. All the other additives will be the same, but the phosphorus will be maybe 300, 400 parts per million less than when it was new. That means the anti-wear additive is being consumed at a rapid rate, protecting the surface from failing. Now, once the surface begins to fail, that's going to change, and you're to see the wear metals go up. So you can have samples with low wear metals at high consumption. Well, again, if I'm jumping from lab A to lab C here, or lab C to lab B, I could falsely, I have a problem. So you don't want to have false negatives. You don't want to have false positives. So you want to try to eliminate any kind of misleading information. That's why it's important. Pick one, stay with one. That's your best bet. And like I said, there's different equipment. So again, same sample sent on a rotating disc method, rotating disc method versus an ICP. Exact same sample, 2 completely different results. Why? Because rotating disc doesn't dissolve the oil. So they don't dilute it. It's just you're literally rotating a disc. The disc goes through the sample and draws it up into an arc, and it burns it. Because that's how usual analysis typically works in terms of the parts per million on wear metals, is you're taking the sample of the oil and you're burning it. And as it burns, everything's emitting light. And we have a spectrometer there that's reading the wavelength of light. And because each element, as it burns, emits a wavelength of light unique to itself, we can look at the intensity of each wavelength and determine how much of that element was in that sample, which is where the parts per million comes from. So that's what's called spectral analysis. Rotating disc, there's no dilution of the sample because it just picks it up. The ICP, we have to dilute it with a solvent because you're spraying it through. So it's one of the things. Rotating disc is slower. It's a broader sample size because it's not being diluted. ICP, much faster, but you lose some of that data, some of the pieces of wear material that could be showing up. So that's why it's important. I said, pick a lab, stick with it, because these kind of small device changes can throw you off inadvertently. You don't want to have that. Here's a good report where we were mentioning earlier how you can see that change in wear metals and how sometimes it will like it, not like it. So this sample right here was the first sample when they changed from the previous brand to the driven DI-20. And it wasn't bad, but it wasn't great. 10 parts per million is really very little on iron, especially for the mileage. Everything here looks really good. But this was the next sample. And you can see that just the same oil, just one sample later, when it has its full chance to work and not have any cross-contamination, it goes from 10 down to 4, from 12 down to 1. How much more effective that oil is performing when that cross-contamination has been removed. And you can see a little bit of that, in this case, from the magnesium, right? So the magnesium right here is the key thing to let you know that's cross-contamination. Because you can see from this sample, well, that driven DI-20 doesn't contain magnesium, or very, very little magnesium. And the previous sample had 147. What's that from? That was from the previous oil that did contain magnesium. So that's one way of knowing when you have a cross-contamination, is having that new oil sample to reference from. You can see it, and then you can see all this results here. And then again, the trend analysis, one great thing you can look at the trend analysis in this case is how effective having your fuel injectors cleaned or using a detergent additive in your fuel can be. So in this case, this guy, he started off, he was going along, he had, 1.6% fuel dilution, which is not bad. You like to see under 2 for street driven cars. But then the next sample, whoa, 2.56. Fuel dilution went way up. So he saw the report, said, okay, I'm going to go out, I'm going to buy a fuel injector cleaner. I'm going to run some fuel injector cleaner through one tank, just one tank, and came back the next time and it dropped down to 9.3. 0.93, right? Less than 1. It was because the fuels he was using may not have been top tier, and that the injectors were getting dirty. They weren't able to atomize the fuel as well. If the fuel doesn't atomize as well, the chances of it vaporizing are less. And then you get raw fuel in the oil, which is what we're seeing here. So you can use that fuel dilution measurement, which again, is where most problems occur, key in right there. And this is a great way of knowing whether or not that injector cleaner is actually doing the job or not. Because if it's doing its job, those numbers will go down. We're in the home stretch. The voice is going to make it. I believe it. Now, as I said before, don't read too much into one number, right? The number one rule is if you get something that's a really far outlier, looks really crazy, retest. And that's not because we're trying to sell you another sample kit. It's because you need to have validation, right? Was there some contamination? Was there some kind of in the test method or sample procedure? If it shows up twice, then you know it's real. Shows up once, it could just have been an anomaly. So then you also want to go back to take not just one number, right? Like in this case, you could say, well, 6 here and there's 6 there. It's the same. Not the same. Add in all the components. Now, let's trend out and normalize by looking at the wear per 1,000 miles. Now we can begin to see a difference that in these flat engines, well, what's normal is going to be maybe closer to around 5 parts per million wear metals per 1,000 miles. You could actually get it down to closer to 2, 2 or 3, just by a few changes of what you're doing for oil. So you want to look at all the numbers and paint that clearer picture. And really the normalizing, it's really the key thing to do. That's really what makes things go. You want to look at all of them as a whole. And as we mentioned before, don't expect the Sherlock Holmes, the CSI moments. There are times where, hey, look, I got all kinds of crazy stuff going on up here. Oh, but guess what? It's positive for water. All right, we had a leak. We had some contamination. That's the reason why these are there. We were able to find it in one sample. Or in this case, you got a big warning flag. Why? 8.7% fuel. Well, that's why the viscosity is so low. It's because it's full of fuel. Well, in this case, there was a dirty, stuck injector, but the guy was driving the car. He had no idea there was a problem. It's a good thing he did it. Now, he probably should have smelled fuel when he took the sample, but he had raw fuel just going in because of a bad injector. So the limitations, as we kind of mentioned throughout this, it only can see particles that are about 10 microns or less. So if you can see it in the drain pan, it can't see it in the oil analysis, which is why cutting a filter open, looking at the filter and looking at the oil as it comes out is an important part of it. You want to bookend and not just rely on what the test result alone says. Look at the sample itself. Use your eyes, take that filter, cut it open, look at it. If you can see it, it's big enough that it can't see it, and then put that picture together, because you can see samples come in and they're very, very low numbers, but that oil looks like metallic paint. All right, trust the metallic paint part to tell you you got a problem. If the oil looks good and the sample comes back, says that everything is good, it is good. The modern LED flashlights will scare the hell out of you if you put them into your oil pan, because they're so powerful that it will make everything reflect back. There's like a Christmas tree going on in there. And so don't do that. Just use natural light as your thing. Don't hit it with that. Other thing is, wear metals are just that, wear metals. So a lot of the modern cars, which I know this is historic cars right now, but modern cars though, there's a lot of timing chains that are made, or timing chain tensioners and stuff that are made out of plastic. Well, used oil analysis can't see the plastic more times than not. There are particle counts, but particle counts don't tell you what it is. It just says there's particles of this size, shape. And in diesels, its particle count's almost useless, and to some degree, because there's literally so much soot. And the darker the oil gets, because particle counts basically use the shadow of the particle to determine it. Dark oils, you can't trust it. So another thing to know too is that most of these tests will not run at all if there's water. If there's a high enough amount of water, it's useless. So if you can see free water in your sample, you're wasting your time sending it in. It's just going to tell you what you already know. You got a big time water contamination problem, and everything's going to look bad. And that's if you can even run it. So keep these things in mind and know that. And with that, I left us some time for questions.
Okay, I'm going to go ahead and unmute. I don't see any questions in chat right now. Let me just recount a couple of my experiences. I was talking with some of you that came in early. After our last talk with Lake about oils, past president showed me his oil analysis for his OM642 diesel. And I have a car with an OM642 diesel, and mine was 140,000 miles, and his was about 115,000 miles. And my wear metals looked a lot better than his did. And we were using different oils. He was taking his to the dealer, and they were putting in the oil that they put into probably every other car in his car. And what he did is he changed the oil I was using, and very quickly in the next sample, the wear metals were down. And it was in fact an oil that was not on Mercedes recommended list. But in that case, the oil analysis showed that we were better off using that oil instead of what the dealer was putting in his car. That's
a great example of using the tool to tell you what's right. Your engine will tell you what it wants. You just have to listen to it. And this is a tool that allows you to listen to what the engine is telling you.
Yep. Let's see. John Bernardi asked, how many miles are on your 240D?
Well, so the odometer was broken for about 10 years. So it says like 180,000, and there ain't no way it's 180,000.
Yeah, my 300 TD has 349,000 on it, but it's getting kind of needy. Radu asked, can we get a copy of this presentation? What I plan to do, hopefully, if Lake will give this to me, is I'll send it out to you all. Sure. And we will also put this recording up on our YouTube channel so you can get a look at it.
Happy to do that.
John Bernardi asked, what is the plus or minus on a typical wear metal result, if it gives 10 ppm, what is the range?
Okay, so that's a great question. So when you see anything on a oil ounce report in terms of wear metal or an additive level, if it's 10 or less, it's basically zero. That when it gets down to that fewer particles, that little bit of light being emitted, it's really hard to have a high level of confidence that that a 6 is a 6 and a 3 is a 3. Now it's 50% difference. I get that, or 100% difference actually. But as a general rule, numbers are single digits is good. Don't even try to discern between single digits. Now, there are some cases where we're in a very, very controlled environment and we've eliminated pretty much every other variable, and we can say, oh, this is a 10 and that's a 20. Well, that's a difference. We can know that. I've even seen some cases where you can really measure the difference between, an 8 and a 4, but that's lab scale, very precision. I wouldn't try that in the field. I wouldn't put that same level on that just because there's too many variables involved. But as a general rule, single digits, they're good. Don't worry about them. When you get, say, between 10 and 20, those aren't to be worried about. They're good. I start getting worried when I start seeing things pop up into the 30s. I really don't like, me personally, I hate seeing anything that's over the teens. If it gets into the 20s, I don't like it. To me, when things are right, teens or less. And so that's my goal that I always shoot for, is I want my stuff to be teens or less. Like I just got a sample back earlier this week on my Boxster, and everything is single digits. I'm like, yeah, that's what I'm talking about. That's where we're doing it right. If it's single digits, I'm good. I'm a happy camper. So hopefully that helps.
Okay, Dean S. asked, quick question, what does a vacuum sampler look like, or do you have a suggestion of which one or type to look for? Thanks for the knowledge.
No problem. I
might
be able to find a picture. I have to get out of my stuff and go look through all my photos to find one. But essentially, you can get them at Summit. You can go. It's a vacuum sampling pump. It just looks just like that. It's like a tiny little bicycle pump that has a little tube out of it and that tube goes down the dick tip or dick tip tube, or it can go into the sump if there's a way you can reach it. And then the bottle screws onto it, and you just sit there and do like this, and it sucks the oil in.
Yeah, I got mine from Blackstone Labs, which is the lab that I've been using for, I think it was like $35, but that was probably 8 years ago.
Yeah. Who knows? In the last year, we want to talk about that. But yeah, most labs, they sell them if you need them. You can buy them sometimes as a kit. But I also know that Summit has them just individually. Like if you already have kits, and you didn't know about it, and you want to just go buy one, they have them there too.
Yeah, Alan sent a direct message to me and asked about the oil that that the dealer was using for that car that we were talking about. I don't exactly know. I think it was one of the mobile ones, but they're not all the same, and that's the key. If you go back and look at our last talk about oil, there's really, even within specific brands of oil, there's a lot of differences in the oil, and you really, especially if you have an older car, look at the spec sheet, see what's in the oil. Mobil One 15W50 is not the same oil as that 0W20 stuff.
No, very different. Even companies like Mobil, for example, and not picking on them by any means, they have, with the same viscosity, they'll have 3 different chemistries between the same viscosity. One could be their extended performance, one could be a diesel, one could be a fuel economy performance, and they're all different in terms of what their chemistry is. And you're right. I think the case is when you go to a dealership and have them change the oil, they're going to be putting in, it can be the same viscosity, but it's the modern additive package for the modern cars. And the classic cars, it's different. The surface finish is different. The metallurgy is different. The older cars tend to like different chemistry. I'll leave it at that. I won't go into the Pandora's box of that.
Yep. Yeah, that was the last talk. But
yep.
Michael Vitesse asks, can wear metals change for older cars versus newer? Meaning, is bearing composition something we should be aware of, like a 1967 Mercedes versus a 1999 Mercedes?
Great question. Those times are going to be a little bit different. So pretty much every car built in Europe prior to 2010, 2011, most of those cars were going to have what we call tri-metal bearings. So you're going to have copper, tin, and lead as the component. And it's the lead tin is the overlay. And the main bearing surface is going to be copper lead. So when you start to see tin and lead together, that's the sign that the overlay is wearing. And that can be from really cold starts. Maybe if you're, say, you've got any kind of cause that would cause the engine not to fire, right? Broken spark plug, something where the engine's just turning over, and it's dumping fuel in there, but it's not cranking. That can definitely get into the overlay because you're not building enough speed to really build that wedge, and you're putting fuel in there, and that kills things. So excessive starting, really, really cold weather starts, you can see some of that copper tin, the tin and lead show up. That's overlay. Don't worry about it. Know it. Say, all right, I got to change my procedure here, depending on what you're doing. Then, starting in 2010, though, the EU had banned lead bearings from their production engines. So at that point, they switched to an aluminum tin bearing. So you won't see lead show up anymore. You'll still see some tin and maybe some silicon. So you've got this overlay of tin over an aluminum silicon bearing. And so that's where you got to kind of look at that a little bit differently. The other thing I know too is bore material. So the older engines definitely were cast iron sleeves, and that maintained. And then you get into some of the modern cylinders that are the plasma spray bore, they can contain some moly and some things like that in there as well. So understanding that, the date of the car will have an impact on that. Like, so just for example, Porsches, they're typically going to be either Nikasil or Alusil cylinders. So they don't have iron. So guess what? What's normal iron for a Porsche is way lower than normal iron for anything else. So we look at them completely differently. Like, it's not even the same set of standards for a Porsche engine because of that. And the same thing would apply to an Audi that's also an Alusil cylinder. So knowing the car and what that composition of the metallurgy of the engine is a very, very important thing to understand. And yes, you will look at an older car because of that different than a modern car.
Okay, well, here's a question. I know what you're going to say to this one. Radu asks, based on the analysis results, can you recommend a certain brand of oil?
No. No, you really have to know, because I can say, hey, you know what? I've had great success with, pick a brand, right? So I'll be a homer. So I worked at Driven for a long time. I formulated everything. So like DI-40 is like one of my favorite oils. So I know DI-40 is great stuff, but that's been great stuff for me, the way I drive and in my cars. That doesn't mean it's going to work for you. The only way it's going to work for you in your vehicle is to do oil analysis and check it, because fuel varies all around the country. It's not the same. There's seasonal blends, and some oils will work better for cars that see high temperatures. Some oils will work better for cars that see low temperatures. Some oils are going to be better for turbocharged cars compared to naturally aspirated cars because there's different additive packages in there. So in the day, I'm not going to recommend any one oil to anybody because there's no one oil that fits everything. It's really about understanding your application first, picking the correct chemistry for your application, and then monitor it via oil analysis, and then make changes as you see appropriate. And I think that's the right path. It's a harder path, but that's the only path to go to really fine tune it. Anything else is closing your eyes, throwing a dart at the wall, and hoping you guessed right.
Yep. Okay. And from John Bernardi, what is the range for a single sample and oil analysis cost?
I mean, you could depend upon how fast you want it, right? I mean, like the NASCAR guys, those guys paying $120 a sample, but they need the results back in 3 days. So they're literally showing back up on Monday at the shop, and they're having their results on Wednesday. So if you need it that fast, you can pay and have everything expedited and get it that. Or if you're just, bottom of the barrel, I want to spend the least amount of money as possible, you can probably find your local Caterpillar dealership and go in there and you probably buy one for $20. Now, who knows when you're gonna get it back? Never get it back. That happened before. And then samples and no, it got lost. That's they're processing. God, I mean, Caterpillar Labs process the highest volume of anybody, but they are the cheapest. So it's got to figure out what that value proposition is.
Okay. Yeah, I pay about $30 per sample, and it takes about 2 weeks to get the sample back, and which is acceptable for me.
Yeah.
Okay. I don't see any other questions. Let me ask you a question. Having watched your series with Ellen Engineering on bore scoring, I was wondering, do you know of any bore scoring issues with Mercedes engines?
No. It's not to sound like a Mercedes-Benz homer here, but they build engines better than anybody else. I mean, they're the first company in the whole world to build an internal combustion engine. Now it's a hybrid, but their Formula One engines were the first engines to ever reach 50% thermal efficiency.
Wow. I didn't think you could do that.
Oh, it's amazing. They've done a terrible job at telling their story. The normal passenger car engine is about 25% thermal efficiency, at the flywheel. A really good turbo diesel is about 35%. Race all the time at 50. They they're north of 50. They don't even tell you how far north they are, but they're at least 50, which is incredible. That is on the level of fine gas turbines.
Wow.
That's insane to have turbine level efficiency in an internal combustion engine. Now, they are ridiculously expensive, ridiculously complex, but they've proven they can do it. And so I have a high level of respect for the engine folks there at Mercedes. They have a long history. They've tended to design things extremely well, and we don't see those issues. I mean, the real bore scoring problem was really down to Porsche cheaping out and going with an Alusil block, just because it bit them in the butt, because the surface finish is too irregular, and they don't have a consistent enough oil retention on the cylinder bore to maintain proper lubrication of the cylinder bore. That's the problem. Mercedes, they were the ones that kind of pioneered on the production level going to plasma spray bore. So yes, they also saw the same challenge coming that Porsche did in terms of Nicosil and things like that, because Nicosil always worked pretty good on a factory level. but they went to the plasma spray bore, where you're basically melting iron and spraying it onto the bore to basically blow in, if you will, an iron sleeve into an aluminum engine. And they have their own patented process for doing that. And it works phenomenal, absolutely phenomenal, to the point that we're actually, other companies are copying that same kind of technology and employing it in production level. And we're even looking at it to put it into the aftermarket because it works that good.
Wow, neat. Now here's another question from Alan. How relevant are the bearing scar wear tests that are popular on YouTube?
Oh my God, thank you for asking that question. Thank you. Not a single bearing test that applies any internal combustion engines at any point. It is all hot garbage. And let me tell you why it's hot garbage. Number one, what they're using is a Timken bearing. They're using an outer race, a tapered roller bearing. Both of those are made from the same material. They're 52-100 bearing steel. There's not a single part, a normal internal combustion engine, that's made out of 52-100 bearing steel. Nothing. And by the way, when you design an engine, you never design a component to run against the same material. You don't run a cast iron camshaft against a cast iron lifter and expect it to live. There has to be a difference in hardness. So you're running these parts are not designed for sliding. They're designed for rolling. And you're running it environment. Also, by the way, doesn't contain combustion. And the geometry of it is not correct. The line contact geometry is completely out of line. So what it's doing is creating what we call an extreme pressure, where all you're testing is the anti-weld ability of the oil. Put in that test Head and Shoulders shampoo. Beat anything you can put else in there. But who wants to put Head and Shoulders shampoo in your engine and go drive it around? But on the bearing test, and most of the additives they're putting in there are either chlorinated paraffin or some type of sulfur-based additive that will boost the extreme pressure properties of it. Which, by the way, contains active sulfur or chlorine will create sulfuric acid or hydrochloric acid in the presence of water. You may be wondering, well, there's no water in my engine. Aha, yes, there is. Every single combustion cycle, we're making water. Yeah. Now it's vapor, but it's still water. There is some blow by. It gets into the oil. And guess what? So now you're going to make hydrochloric acid or sulfuric acid in your crankcase, eat your engine alive. I wish they would ban the sale of those stupid bearing testers. They're the worst thing ever created. Sorry for the rant.
Tell us how you really feel. Okay.
Yeah, exactly. Yeah.
Okay. Well, that was all the questions there. I think that was really a wonderful presentation. I really thank you for doing that. I think this is what Mercedes-Benz Club of America folks really need to hear. And as you know, I'm really an advocate for oil analysis. I do it every time I do an oil change. And so I just really appreciate your spending your time with us today and talking about that. Like, it's just a great presentation.
Thank you for letting me come and talk. And like you said, it's a really low cost investment for, $30, $35 for a sample. You do that once a year, that's cheaper than most people's copays.
Yeah, that's for sure. Okay, well, just a commercial for our next tech session. We won't have as illustrious a speaker as Lake talking on the 20th of July. I think I'm going to do a presentation on changing radiators and water pumps on M113 engines, specifically my couple of CLK 55s. So we'll talk a little bit about that. for those of you that want to get into the details of those fairly straightforward jobs. But in any case, we'll let you know when we get the video up, and if Lake will be kind enough to send me the presentation, I'll send a follow-up email out to you so that y'all can peruse on it over your own time. I thank each of you for coming, and again, Lake, thank you very much for presenting with us today.
No, thank y'all for inviting me. I appreciate it. Have a great weekend.
All right, thanks everybody. And for some of y'all, I'll see you Saturday.
Yes.
Robert.
I'm trying. I have, speaking of radiators, I have a leak and I'm trying to get a change, and FedEx is screwing up. So it'll be close.
Oh, I'm sorry to hear that. What are you getting? A hose or something?
I wish it was a hose. No, it was a radiator, had a minor leak, but nevertheless a leak. So I'm getting it changed out, and I just got bad news from Federal Express. They aren't delivering until tomorrow sometime. We'll see. We'll work it out. Don't worry.
Yeah, it's I've done radiators on both of my CLK 55s, and track use kind of showed that on those radiators, it's a plastic tank on each side and a metal core, and the seam between the metal tank and the core just starts going bad at, someplace up in the high mileage. And the first time I used one of those CLK 55s on the track, it was spraying coolant everywhere.
Well, anyhow, we'll work this out. This was good. Thank you. And I guess, is Lake going off? What a great name. Lake Speed. You got to be kidding me.
Yeah, great name for a racer. Huh?
Yeah, Lake Speed.
Okay. All right. Well, hopefully we'll see you Friday. And everybody else, thank you for coming.
You're welcome. Thanks.
Ruben, you still there? Looks like you are.
Yes.
Okay. I was seeing if Ruben is still there. I thought he was going to sign off. All right. Well, anyway.
Over and out.
All right. We'll see everybody. Bye-bye.
Bye-bye.